Right, today we will learn about the analysis of the fire accelerant. Okay, so which is our chapter 5, if I'm not mistaken. Right, I will divide this particular chapter into two parts. Okay, so the test will enter until the first part. So the first part will cover until sample preparation. So it's up until sample preparation. Alright. So just as introduction, okay, for any kind of analysis, okay, in the lab, of course we need to prepare the sample. Okay, preparation of the sample is one of the important step. Okay, might not be the first step, but one of the important step. Okay, so the preparation of the sample will take a lot of time. Okay, then followed by the analysis, and then we need to provide the discussion. So not only we providing the raw data or results, so we need to provide them the interpretation as well. Okay, so this is very important in the fire investigation. Okay, if we focus on the fire debris analysis, okay, not the other analysis, we need, based on the analysis, we can provide, okay, the cause of fire. Alright. Okay, so here are the steps in analysis. First, you need to understand and define the problem. Why we need to understand and define the problem? Because different cases may require different sample preparation, for example, or may require different type of instrumentation, for example. Okay, so we are required to perform different procedure in case our sample is different. Let's say, for example, if the sample in the form of liquids, so it has different sample preparation compared to the sample that has a solid form. Okay, the next second one is the literature search. Okay, after you understand, okay, the problem that you have, then you do the literature search. So normally for the services lab, okay, services lab, they will try to focus on finding the standard method. Okay, because the standard method is one of the procedure that been accepted around the world, and most likely, okay, commonly, okay, will be first prioritized to be accepted in the court as well. Okay, then after you have performed the literature search, you combine or you compare several procedure, then you select the best one. Okay, you select the best analytical methods that you can perform in your laboratory. Okay, why I say that sometimes you don't have the GCMS, so you only have the GCFID, so you can choose the best suitable method for GCFID. Let's say, for example, in your lab you don't have the rotatory evaporator, so you cannot choose that particular literature search. So you need to find, okay, select the procedure which suits, okay, that can be done in your field of work. Okay, then of course you start to sample or sample preservation or sample preparation. Okay, so most of it, okay, we would like to eliminate interference. Okay, remember that in the fire analysis, it's not really important for us to identify the quantity. The most important that we can confirm the presence of that particular accelerant. Okay, alright. Then after that we have done the sample pressure, we perform the analysis. Okay, we need to compare the results with the standard method, or you need to have the quality control, so you can check either your instrument is working or not. That is one of the important aspect, because in court they will ask, okay, how do you perform, okay, the calibration and validation of the instrumentation. How do you know that the instrument is working very well? So you need to compare the results, okay, with the quality control, so the standard method. Okay, then you need to apply require any necessary statistical methods, okay, to verify the results, okay, to produce the result. Okay, so you apply required statistical techniques and verify the results. Okay, and at the end, of course, you do the reporting. So in this particular reporting, you need to provide not only the raw data, but you need to provide your discussion and also conclusion. Right, so now let's say, for example, to understand and define the problem, okay, so you need to learn as much as possible about the problem that you face. Okay, for example, you need to understand what is the problem you would like to investigate. Either it is quantitative or just a qualitative analysis. Okay, so you need to understand what kind of the sample. Okay, what is the limitation of the sample. Okay, how the sample is preserved or how the sample is collected before that. So you need to understand as much as possible. So how we can understand what is the problem. So to understand is what is the problem, we need to understand what is the objective of your analysis. So they are correlated. Okay, so the objective, okay, must be correlated to the problem that you face on by providing the objective that are able to solve the problem. Okay, so usually if the problem is okay, you can have a very good objective of the to solve the problem. Okay, right. Then you need to understand as well who will use the information. Either it's the common person, of course, in the case of forensic analysis. Okay, is required by law. Okay, it's required by the court. Okay, so you need to be very accurate. Okay, you need to be very confident that your result is reliable as well. Okay, then you need to understand that how many samples need to be analyzed and when will the result be needed. So this, okay, will also contribute on how, okay, you are conducting the analysis. For example, if the sample is too much, okay, so you might need to perform auto sampling analysis. Okay, so when will the result be needed? Okay, that is very important as well. So you can organize, okay, how you can do the analysis and providing the reports in a timely manner. Alright, let's say you already understand what kind of the problem you need, then you start to do the literature search and method selection. So you need to do that. Okay, so you need to do some readings. Okay, so you need to compare between several standard methods, or you might need to compare between different journals. So main source, okay, for the forensic analysis, of course, is the standard method. So here is the example of the standard method that you can find. Okay, for example, coming from the STM method. Okay, here is coming from the AOAC. Okay, alright, so you can find several other standard method from different organization. As long as it's a standard method, so we don't need to worry about it. Okay, alright. So the standard method is more superior if you compare to the textbook. Okay, is more superior compared to the journal, and even far more better compared to, for example, obtaining for just a mere website. Okay, so that's why the standard method, okay, is really important. You need to understand that the standard method is the method that has been proved, okay, and been tested at several labs, okay, and has been validated, has been optimized. Okay, so and that's why standard method is the best, okay, out of the others. Okay, it has been validated, has been optimized, okay, and commonly accepted in court. Okay, alright, so that's why compared to the other kind of literature, standard method will be the best. Okay, so is there any situation that you can use other kind of the method other than standard method? Can you use journal? Okay, so in the situation where standard method is not available or no specific standard method for your particular matrix or situation, so you can refer to the journal. Okay, so remember that in the forensic, okay, we have two I'm not really remember about it. Okay, so we have as long that we can provide empirical study, empirical results, okay, so the method should be accepted. Okay, right, so here is the question: can you use in-house method? Okay, without strong justification, so we are really discouraged to use the standard method. You use the in-house method, okay, unless there is no standard method available, then you can use the published method. If the published method is also not available, okay, you can use the in-house method. So what is the in-house method? Okay, so standard method is the method that been produced by a standard organization, so it has been validated and optimized. Okay, why the published method? Okay, by all the researchers all around the world, by the academicians. So in-house method is within your lab. Okay, you are optimized and validating that particular method. Okay, so usually the in-house method is used. For example, the standard method and published method is not available for your particular situation. Let's say for example, previously there is nobody yet to analyze, okay, drugs, for example, in the liquid vape. Okay, that is the particular example of situation. Okay, so in that situation, there is no available standard method, there is no published method available, then you produce your own in-house method. Let's say for example, you find new kind of the accelerants. Okay, let's say for example, purple phosphorus. Okay, purple phosphorus. Okay, maybe it's not still present. Okay, maybe we have the purple phosphorus. So there is no standard method available for that particular compound or that particular analyte. So you develop your own method, so which you use in your own laboratory, that we call as the in-house method. Okay, so if in-house method is the only choice, so you need to perform full method validation. Okay, you need to perform full method validation, so you need to adhere whatever requirement by the ISO, okay, 17025, ISO IEC 17025. Okay, what you need, what is the list of requirement that you need to perform for full method validation and optimization.
Okay, so for the fire analysis, okay, so we focus on the ASTM method. Okay, ASTM stands for American Society for Testing and Material Standard Method. So right now I divided into preparation and instrumentation, and right now I focus on the sample preparation only. So for the instrumentation, we will go after the test lah. Okay, we will look into this particular instrumentation after the first test. Okay, alright, for the sample preparation, okay, for first sample preparation, okay, so there are several other kind of the sample preparation. We can have the solvent extraction, we can have the static headspace, okay, we can have the dynamic headspace, passive headspace, and SPME. Okay, so for the sample preparation, actually I divide into three, which is directly by using solvent. Okay, so we need to use liquid solvent now. Of course, we need to use solvent. The second one, okay, we use headspace. Okay, the headspace, okay, actually the fiber will also is one kind of the headspace, but I separate them because this particular headspace, okay, this three headspace doesn't use fiber. Okay, doesn't use fiber. So the fiber is quite advanced technique where we use the SPME fiber, solid phase micro extraction fiber. So later you can click this particular link, so they can provide you to do specific standard procedure. Okay, right. Okay, so now let's go to the sample preparation. Okay, what is sample preparation? Okay, sample preparation is where we need to bring the sample into the correct form. Okay, so the correct form is not only the correct size, but we need to prepare them so we will not damage our instrumentation later on. Okay, so we need to bring them into the correct form and the correct size. Okay, let's say for example, okay, we need to we receive in the form of powder, so we need to prepare in the form of liquid, so we need to bring into correct form. Okay, let's say for example the size is too huge, they get you about 1,000 liter of sample or 100 liter of sample, but you only require few mil of the sample. So how you want to prepare them into the correct size? Okay, so the sample preparation is the one of the most laborious, time consuming and error prone. What is it by most laborious? Because in the most step of the analysis, this is the hardest one lah, because you need to perform a lot of works. Okay, and of course if you have a lot of works, it will be also time consuming. Okay, and also do you have error prone, because as the steps taken required become more and more, so it will increase the possibility of the error, okay, to also involve. Okay, so we will increase also the amount of the error can be there. So for example, you have only one step, so the error that will be due much less compared if you have 10 steps in your sample preparation. So that's why if possible, so you minimize the number of steps taken, okay, in the sample preparation. So we have the pie chart over here. So if you look over here, sample preparation is about 61% for the entire of analysis. So sample collection is just merely 6%, sample analysis is about 6%, and at the end is data handling and also the production of the report. But most of the times require a lot of the sample preparation. So why sample preparation is required? Okay, first you need to remove the interference. Okay, why we need to remove the interference? Okay, you need to ask that particular question in your mind. First, you want to make sure that you obtain a very clean, okay, analysis. For example, here before the preparation and after the preparation. With the contamination, you have a lot of noise that disturb the analysis. Compared to this one, it's so clean, so it gives you a very good result. Okay, it gives you very good result. So if it gives you very good result, so it can give you very better accuracy. Okay, so if we compare between these two, we can see clearly the peak of interest compared to this one. So when the baseline of noise also reduced because of the removal of the interference, it will increase the sensitivity of the analysis. Okay, it will increase the sensitivity of analysis, and of course your results will become more reliable. Okay, the second one is the concentration adjustment. Okay, especially in the fire analysis. Okay, the amount of the accelerant found highly to be in the trace amount. Okay, so your accelerant might get diluted in the water, okay, might diluted or seep into the soil, so you need to bring that, okay, you need to concentrate into small volume, okay, so it become more concentrated lah. Okay, let's say for example, let's say you collect from 1 liter of water from the puddle of water, you bring using the SPE, then you concentrate into 1 ml of solution. Okay, so in the concentration adjustment, it's not necessarily that only from dilution to concentrated. Okay, there are some situation then that your sample is too concentrated. Let's say for example, you receive what we call a canister that has the accelerant. Can you just inject that any liquid from that particular canister directly into the instrumentation? So you cannot do that. Okay, in that particular situation, okay, because it's too concentrated, you will not very good result. Okay, because it's too concentrated, your instrument cannot reading it, so you need to dilute them. So there are two situations. First, dilution. Okay, you need to concentrate them. Okay, the sample is too diluted, you need to concentrate them. The second situation, that the sample is too concentrated, that you need to dilute them. Okay, then the third one, the instrument compatibility. Okay, for example, okay, in the GC, you need to prepare the sample in the form of liquid or gases. Let's say the sample coming from solid debris. How can you prepare? You cannot simply just using a mortar and pestle, okay, make it into powder and just inject them directly. It will damage the instrument. So you need to bring them into the correct form, separate them from any interference, okay, and collect the best thing out of them, so it will not damage the column. So now let's go one by one. Okay, the first one is the solvent extraction. Okay, so it is also known as the solid leaching extraction. We call leaching lah. So what is called leaching? Okay, so the sample is solid. Okay, and the extraction solvent is solvent lah. Okay, basically here is the example of the leaching. Okay, I believe that all of you drink coffee, maybe some of you love coffee, so the principle is about the same. So how do you extract the coffee from the powder, from the coffee beans powder? So you use the hot water, okay, to extract the coffee from the coffee beans powder. So you don't want to eat the coffee beans. Okay, nobody want to eat the coffee bean powder because we cannot consume them. So that is quite similar to the instrumentation. So you leach, for example, from the fire debris, you leach them into the solvent, and then you use the solvent. Okay, you extract from the solvent. Okay, then you run under the instrumentation. So the solid liquid extraction or the solvent extraction, okay, allows soluble components to be removed from solid using a suitable solvent. Okay, so let's say for example again, you put your sample over here and then you drip the solvent, or maybe you just immerse them in the solvent and then you filter them later. So your analyte is soluble in that particular solvent, so you can use that particular solvent for the instrumentation. So in this particular principle, you need to choose an appropriate solvent. So in this particular solvent extraction, there are two major steps, which is contact and separation. Okay, the first principle, okay, you make a contact between a solvent and the material of extraction. Let's say in the case of the coffee here, you put water and then it come into contact with the coffee bean powder. Then here, after that, you allow for the separation. So you only want to separate the water. So how can you separate the water from this particular solid? So you can do simple sample filtration. Okay, you can use filtration, or maybe you can use distillation. Okay, you can distillate them. Okay, in fire debris, okay, we need to understand that the sample is volatile. And then you can use the solvent and then you can vaporize them and then collect the vaporized solvent, okay, through a distillation condensation. Okay, distillation and condensation. Okay, right. In the solvent extraction, there are a few types of contact techniques. Okay, the first one is the single batch. Okay, the second one is multiple batch, and the last one is continuous. What is mean by single batch? Okay, single batch is the single time extraction. It means that you just put the coffee beans and then you put the water and then you spread them. That's all. Okay, so what happened that in multiple batch is that, for example, first you mix them and then you separate the coffee beans and the water, and then the water you collect in the other bottle. The coffee beans you are further extracting by another batch of water, and then that batch of water you add with the previous one that you have collected. Okay, then you combine them. Okay, it has been proven that the multiple batches, okay, is much better compared to the single batches. Okay, so this is the single batch and multiple batch of solvent extraction. Okay, the last one of the solvent extraction is the continuous. Okay, so I believe you guys have learned about the Soclete extraction method. Okay, in this particular procedure, you have the solvent over here, you put sample over here. So you boil the solvent will goes up to here through a process of vaporization, and because of the condensation process over here, okay, your solvent will drip back to the sample, and then it will goes down back to this particular flask. Okay, round bottom flask. So after several hours, the process continuously occur. Okay, it goes up, goes down, goes up, goes down. Okay, so your analytes of interest will be concentrated to this particular area. So what is the correct way to use the best solvent system to this particular analyte? Okay, so you need to use the best solvent system, that is your analyte is soluble within that particular solvent, and then the solvent here must be volatile enough. Okay, must volatile enough that it's capable to volatilize and vaporize and then condense back to this particular sample. And then you need to make sure that, if possible, okay, the boiling point of the solvent is much more lower compared to the boiling point of the sample. If not, the boiling point if the boiling point of the sample is lower, if the boiling point of the analyte is lower, it will get vaporized and lost to the surrounding. So here is the example from E1386 based on that particular standard method. So what the standard method suggests, so first you put the debris inside of the container and then you put appropriate solvent. Okay, here they use the hexane. Hexane is non-polar. Okay, so most of the time that the analyte for the fire is made of non-polar analyte. Okay, non-polar analyte. Okay, but it can also be polar. Let's say for example they burn your house using alcohol lah, but the accelerant, let's say coming from kerosene, diesel and petroleum, they are non-polar. It's not necessarily that you need to use hexane. Okay, let's say for example your analyte is methanol, for example, or your analyte is ethanol. Okay, because that is your analyte of interest, so you need to use polar solvent such as acetonitrile, for example. Okay, for instance, so here he put hexane, okay, add to the solvent and mix the sample thoroughly. So they use the vortex process, and then after that they allow for decantation of the solution. They take the top the solvent and then they can run for the instrumentation. Okay, so what are the advantage of this particular procedure? Okay, so it's very sensitive procedure. It means that even though the residue is small, we can still extract them. Okay, alright. It's also useful for extraction from non-porous surface. Okay, so you can extract from non-porous surface such as glass and metals, well suited to the samples that are not suitable for heating. Okay, so in this particular solvent extraction method suggested by E1386 STM method, okay, let's say for example it's not suitable to be heated, okay, because it's too has a very low volatility. Okay, so you can use a solvent extraction, so no heating are performed. Okay, so the sample will not get lost. Okay, so when we have the advantages, of course we have disadvantages as well. The method is not specific, so the method is not specific to that particular analyte. Remember that in your debris you can have other kind of the interference as well. So what happen is that it will extract them as long it's soluble inside of the hexane in that particular example. Okay, the extraction require good selection of solvent, so you need to choose the right solvent so it can soluble in that particular solvent. Okay, right, the extraction may require pre-concentration process. As we see before this, that you may require a number of solvent. So the number of solvent, okay, because of high volume of the solvent, your sample might get diluted. Okay, so as your sample, okay, might get diluted, so you need to pre-concentrate them. Okay, right. Then other disadvantage that this is a destructive sample. Once you do the extraction process, you cannot further extract anymore. Okay, because it's directly in contact, so it's destructive technique. And of course it's not a great method because you need to use a lot of solvent. Okay, the solvent might be harmful as well. Right, now let's go to the second what we call extraction procedure. Okay, which is the second types lah, not the second one. Okay, the second types. Okay, so the second types of the procedure is headspace extraction. Okay, so what is a headspace extraction? Okay, headspace extraction is when we have to extract the analytes and then we need to isolate them in the headspace. So the headspace is the empty space over here lah. So we can separate our analyte of interest, okay, from the solvent matrix. Okay, from the matrix, so it can remove the interference as well. So the requirement of it that your analytes must be able to be volatilized and then goes into headspace. So what they are usually do is that after they put inside of the suitable container, they close it. Of course you need to close it, if not you cannot contain them in that particular headspace. They will go to the surrounding, so you close them and then you heat them, and then your analyte will go to this particular gas phase, or we call the heat space. Then we will collect your analyte through this particular phase and then run in the instrumentation. Okay, right. So in this particular principle also, they involve the equilibration or equilibrium between the sample and the headspace. So after a while, everything must reach the equilibrium, yeah. Okay, so after a while, after 5 minutes for fittings, okay, no analytes can be transferred anymore to the headspace, okay, because they reach the equilibrium, okay, because they reach the what we call the maximum condition of that particular parameter. So they will get accumulated in this particular headspace, and then you can collect them, and then you can start the analysis. So under headspace, you have a lot of headspace, okay. So you have the static headspace, dynamic headspace, and passive headspace, okay. And also you have the SPME, okay. SPME can also be headspace, can also not be headspace as well lah. Later I will explain lah, okay. Alright. So before that, I forgot to explain that not normally lah, okay. In the beginning, they developed the extraction method using solvent extraction, okay, because of the problem with the interference, okay, okay. So they want to isolate the analyte of interest to compared to the solvent matrix. So they want to isolate the analytes of interest from the solvent matrix. So they come up with the idea of headspace, okay. But the problem with the headspace is that sometimes it require large setup, okay. And that of course some of the procedure over here, the analytes is not going be concentrated, okay. That is some of the issue. So they come up with the fiber, okay. So the fiber not only able to separate from the matrix, but can also concentrated the analytes, okay. Because in the analysis of the accelerator is require us to obtain a very good result, which is reliable and able to be detected. So now let's focus on the headspace here, the static headspace, dynamic headspace, and passive headspace. So let's go for the first headspace. Alright, so let's go for the passive headspace first, okay. So the passive headspace is the first among the first lah, okay, being developed for analysis of accelerant. So what they did is they need to have this particular closed container, okay. The container must be closed because you don't want to have your analyte to lose into the surrounding. And then you need to put a charcoal strip. The function of the charcoal strip is to absorb the analytes. And then you need to have the heating mantle, okay. You need to have the heating mantle over here. So what happens is that they will heat this particular mantle for 60 degree and above, okay, more or less, okay. It's about 60 degrees Celsius for about 2 to 24 hours. So the analyte will get volatilized and absorbed into this particular charcoal, okay. Remember that most of the accelerant is non-polar, so they will absorb inside of the charcoal, okay. But the problem is that this particular method, okay, one of the disadvantage lah. So it can only collect effectively for the non-polar compound because the charcoal is non-polar. Of course, we say that diesel, kerosene, okay, that are example of non-polar accelerant. Let's say for example we encounter with the polar accelerant such as the methanol or ethanol burning, okay. So this particular procedure might not be sufficient, okay. So after the analyte has been vaporized and absorbed in this charcoal, so we can use the charcoal and then we can dissolve them lah. Not dissolve lah, we can dissolve, okay. We can dissolve the analyte here into the solvent and run under instrumentation. So later we will go to the principle, okay. So the first principle, there are two principles over here. The first principle is absorption. The first is the absorption process. The analyte, okay, vaporized and absorbed into the charcoal, okay. And then the second principle is desorption, where you put the charcoal strip inside of the solvent, you shake them, okay. So the analyte will dissolve in this particular solvent, and then what can you do is that you can run under instrumentation. So this is how you do, okay. So you choose a separate container, you put the sample debris inside, and then you put the put the carbon strip, and then you close the container. Then you heat them for the absorption process, and then you transfer into the appropriate solvent, and then you can inject this particular solvent inside of the suitable instrumentation, Okay, so this is what method has been described by 1412. So I believe this is quite good example for you for the your assignment. Okay, so now let's go to the advantages and disadvantages. For the advantages, is suitable for low concentrated sample, so because it will get concentrated in the charcoal straight. Okay, the simple resource procedure, not a lot of work. Okay, but of course it will take a lot of time lah. Okay, so it will also remove non-volatile interference, so we collect only volatile analytes. Okay, of course we will have also interference that is that is, for example, the polar but volatile. Okay, let's say for example, okay, that's an example. But we can at least remove non-volatile interference. Okay, the method also is non-destructive. Okay, so basically you can extract again and run again. Okay, for disadvantages, okay, as I said before, it will take a long of time. Okay, because it will require 2 hours to 24 hours. Okay, the analyte might stay at the absorbent, so it will not be able to be dissolved, so you need to choose a very good desorption solvent. And then potential sample degradation because of the heating process, okay, and not suitable for quantification. For this one, I don't really worry about it, okay, because in their fiber-based analysis, quantification is not really important. Right, so now let's go for the static headspace extraction. I'm not really sure if you guys remember, for when we have the visit to Jabatan Bomba, basically they use the static headspace extraction method. Okay, in this particular principle, they have two principles. Okay, which is they have the heating process where they heat the vial. Okay, of course you need to close the vial, and then the analytes goes to the headspace, and then you put the airtight syringe, okay, and then you pull them into the airtight syringe, and then you can inject to the suitable instrumentation. Okay, so here how you do it: you put your analytes, okay, and sample matrix over here, and then you will heat them. Okay, you will heat them, so your analyte of interest will go to the space area. Okay, and then you take a portion of this particular headspace area in the analyte instead of this, using the gas tight syringe. Okay, gas tight syringe, then you can inject to the instrumentation. Okay, most of the time for the fire debris, as you have looked in the Jabatan Bomba, okay, they use the GCFID, which is they use gas chromatography instrumentation. Okay, right, so here is the static headspace extraction. Right, so if you still remember that it has been done at the Jabatan Bomba, so basically the sample is collected inside of this special plastic bag. So they will heat this first, and then they will absorb them into the airtight syringe. Okay, and then you can inject this into the instrumentation. So there are a lot of advantages. Okay, it's non-destructive. Okay, we can still analyze for second or triple time. The simple the procedure is also simple, so there is not a lot of procedure, so we just require to heat them, okay, and extract them. Okay, so it can be applied so many type of the sample. It can be for the solid, powder, high viscosity liquid, so it can also be done. It can minimize the matrix interference, especially for non-volatile analytes. Okay, non-volatile interference. Okay, and is selective to volatile analytes. For this disadvantage is very limited sensitivity. Okay, if we compare to the passive headspace extraction, where it gets concentrated inside of the charcoal, but in the static headspace you don't have any charcoal to absorb them and concentrate them to the charcoal, so the sensitivity is quite limited. Initial cost setup also is quite high because the airtight syringe is quite expensive as well. Okay, reproducibility issue to the temperature and so on lah, but I don't really worry about this because we don't really do the quantitative analysis. Okay, and then less volatile compound can be hindered. Okay, let's say for the compound that is less volatile, so it's quite difficult for you to collect that inside of the airtight gas syringe. Right, so now let's go for the next one, the dynamic headspace extraction. Okay, the dynamic headspace extraction developed to counter the problem with the static headspace extraction, where the static headspace extraction is that it doesn't have anything to concentrate or to absorb the analyte, so the sensitivity is quite limited. Okay, compared to the passive headspace, also the sensitivity might not be that good. Okay, so they want to increase the sensitivity to the far more superior level, so they develop the dynamic headspace extraction. So when we call the dynamic as dynamic, it means that it involve a flow, it's not static, a flow of extraction. So what happens is that here, okay, you have three main principles. The first, you have the heating process. Of course, you have learned about it. So you heat them to volatile your analytes, and then you do the dynamic absorption. So basically you blow the nitrogen gas, okay, to this particular chamber or vial, okay, and then it will flow the analyte of interest, which is you have volatilized them into a charcoal, okay. Alright, and this particular charcoal cube, okay, is concentrated into of the charcoal, and then you can do the desorption process in this particular solvent. If you believe that, okay, if we look at the passive one, you need to dissolve in the solvent, right? What happen? It will get diluted. Okay, so what can you do that also? You can put inside of the special chamber, okay, directly. You can put inside of the special chamber directly, and then it will get heated out, and then the analytes will get dissolved. Okay, so in this particular dynamic headspace extraction, okay, for the desorption process, you can have two. You can have solvent desorption or thermal desorption. For the solvent desorption, you put the charcoal inside of this particular solvent, and then you inject the solvent. Okay, for the thermal desorption, you can put the charcoal directly inside of the chamber, then we get heated, and then we go to the column. Okay, so this is a very advanced method, and then of course very expensive as well. Okay, right, so here is the procedure. So the sample is placed in the appropriate container. Okay, the container is linked to the gas and the adsorbent tube, which is your charcoal, and then this container is heated and increase the vapor pressure. Then you flow the nitrogen lah. You flow the glass of nitrogen, so the analyte, the vaporized analyte will get flow into this particular charcoal, and then you can do the desorption process. Okay, so here is the desorption process for the thermal procedure. Okay, here is the desorption process for the thermal procedure. So basically you have this particular TDU liner. Okay, you have this TDU liner, is very specific liner. So you put over here, so it will get absorbed to this particular absorbent. I think the flow is quite similar. So then you put this particular liner into the thermal desorption unit. Okay, so it will directly inject to the column. Okay, so you can separate the non volatile interference, and then you can inject directly to the column without dilution of the sample. So a lot of advantages. Okay, right, so you separate the interference. Okay, analytes get concentrated over here, so you can concentrate your analyte, and then you can inject directly to the column without any dilution. Okay, right, so you need to understand the procedure. Okay, so here is the advantage. Very sensitive compared to the what we call the passive one. The passive require dilution into the solvent, so it's quite difficult because you get diluted and reduce the sensitivity. Okay, static also doesn't have any solvent to concentrate them, so now you have the dynamic headspace. It's very beneficial, and versatility to many types of sample, as I mentioned before, minimize magnetic interference as mentioned before as well, and then very selective to volatile analytes. So the best thing about it is very sensitive. Okay, the problem with this particular extraction procedure is quite destructive, because once you do that, you cannot re-extract from the same sample anymore. Okay, and the initial cost setup is quite expensive, especially the TDU unit. So it will cost you 100,000 of ringgits or tens of thousands of dollars at least. Okay, it can go to $100,000. Okay, so reproducibility as before this, so I don't really bother about it, and less volatile compound can be hindered as well. Okay, right, now let's continue on the last extraction method, which is the solid phase micro extraction method. Okay, previously we have learned about the solvent extraction methods, which have a lot of disadvantage, including, okay, you will not be able to remove the interference effectively. The analytes will get diluted as well. Then you also have learned about the passive headspace passive headspace extraction. But the problem with the passive headspace extraction is that, okay, at the end you need to dissolve in the solvent, so your analytes will get diluted as well. And then you have the static headspace extraction. Okay, the problem with the static headspace extraction, the problem is that the analytes will not get pre-concentrated, so the sensitivity of the analysis will get reduced. Then we have the dynamic headspace extraction. Although it can increase the sensitivity of the analysis, but the problem with that, it will disrupt, okay, your sample. So this particular solid phase macro extraction will cater those problems, which is it's capable to eliminate the interference, okay, avoid dilution, increase the sensitivity of the analysis. And of course, compared to the dynamic headspace extraction, okay, it's much more convenient for us, okay, and the setup is much more cost effective compared to the dynamic headspace extraction. So if you look over here in the solid phase micro extraction, it's utilized the fiber SPME syringe. Okay, so SPME syringe, there will have a fiber inside. So there are three main principles, which is the first one is heating. I think you have heard it about so many times. Then you have the adsorption process and thermal desorption. Okay, so what can you do is that you can have two different settings for the headspace. SPME either is headspace or is the immersed SPME. So you can have a direct immersion, and then you can have headspace extraction. Okay, so you can have two different setup of the SPME. First, direct immersion, and then you have the headspace SPME. So for the arson analysis, for the fire debris analysis, normally we use the headspace SPME. Okay, right, so that's why I'm separating the SPME alone, okay, under the fiber. So I don't put it under the headspace, because it can be utilized for two, which is the direct immersion and also the headspace. So first you need to heat, okay, which you have learned it so many times before this. So you heat the sample container, so your analyte will go into the headspace. Okay, you go into the headspace, and then you put the syringe, and then you let the fiber absorb the analyte. You let the fiber absorb the analyte until they reach the equilibrium. Okay, of course the fiber also will have the maximum limit how much they can absorb, so it also has the equilibrium. Then you can extract the fiber, okay, and then you can run under GC by dissolve the analyte under thermal desorption. So this is much common, so you don't have to need thermal desorption unit, so you don't need to have additional cost on that. So you need to have only additional cost for the SPME fiber only. Okay, right, so here the principle is that based on the equilibrium established among the concentration of analyte in the sample and the headspace of the sample and the polymer in the coating on the fused silica fiber. So first, your analyte will get heated, and then they will reach the equilibrium in this particular headspace. Then it will further what we call equilibrium with the fiber of the analysis. Analyte absorb, okay, the amount of analytes that can be absorbed inside of the fiber depends on the type of the coating and also the thickness of the coating. So there are two modes which we call as the direct immersion and also the headspace version of the SPMEs. Okay, for the arson analysis, usually they use the headspace. So how does the SPME work? First, okay, right, so you need to draw the fiber into the needle, so you don't what we call push this particular wire with the needle, because the fiber you don't push what we call the syringe with the open fiber, because if the open is the fiber is open, okay, it is easily break, okay, because the fiber is so fragile. So first you store the fiber inside of the needle, okay, and then you can pierce, okay, the septum, okay. We have the septum over here made of rubber, okay, so you can search later what is the septum. So you push the needle and then you let the fiber out, okay. You can expose the fiber at the head space, okay. Then you extract the fiber inside, okay. Make sure that the fiber is inside before you extract back the needle. If not, the fiber will get break also, okay. Then you extract the fiber, then you extract the needle then you put in the GC injection port, okay. The absorption equilibrium can reach from 2 minutes to 1 hours, okay. So the time required is much more less compared to the, for example, passive expansion, right? So it's very good as well, okay. Then you can inject into the injector. So this pictures. So again, so you have the SPME device, okay. Here you have the fiber coating actually stored inside of this particularly protecting cartridge needle, okay. So you can extract them out, expose them out, and then you can extracted them back in, okay. So then after you have put inside of the container, you can expose them out. So like I said before, you can have two version of the SPME style, okay. You can perform the direct immersion, you can also perform the headspace version, okay. So depends on what kind of the situation you want to approach in. Then you can extract the fiber back into this particular protecting or cartridge, and then you can put the syringe inside of the desorption GC in the GC introduction system, okay, as usual lah, as a normal syringe. Then you can expose back the fiber and then you can inject, okay, the sample to get the result of the analysis. Right, so the desorption step is similar for GC and HPLC. For HPLC, of course, they will flow with water, but for GC, they will do the thermal desorption, and by heating the injector, your analyte will be vaporized by the flow of the nitrogen. It will flow your analyte of interest inside of the GC column, and then it will reach the detector, okay. I think it's quite similar to what you have learned in the forensic analytical instrumentation. So make sure that you need to little bit revise on that, because we will not touch into detail, okay. But of course we will go after this, okay. Alright, so here is the advantages of the SPME. Is very simple, effective absorption and desorption technique, okay. And it's also is very sensitive as well, okay. Can eliminate the need for solvent for complicated apparatus. So it's eliminate the need of solvent, so it's very green, okay. It's very green, okay. So compatible with analyte aspiration detected by GC or the HPLC for this particular situation for GC lah, okay. Why we need use GC? Because analyte of accelerant usually volatile, okay. So it reduce the interfering background, okay, right. Make the analysis much more reliable. It is cost effective, okay. Although the fiber alone can cost you around, a single fiber, it can cost you around 1,000 ringgits, and the syringe also cost you around a few hundred ringgits, okay. The syringe can use multiple times, so you no need to worry. Only the fiber is the thing that I need to worry about, because the fiber, okay, because it's quite expensive, 1,000 ringgits, and it's quite fragile, okay. But if you take care it very carefully, it can last more than 1,000 injection. It can last more than 1,000 injection. It means that per injection cost you around 1 to 2 ringgits, 1 to 2 ringgits, okay. But you need to be very careful, okay. If I have time, I will show you later, okay, the injection, the SPME fiber, okay. I will try to bring to the class. So what are disadvantages of the SPME? Alright, so some drawbacks: incomplete desorption, okay. What happen that you need to, before you can have the next preparation of the sample, okay, so you need to dissolve everything in the syringe, So let's say if you have incomplete desorption, so you can have contamination from previous injection, you can have contamination from previous injection. So that's what we call the carryover problems, where incomplete desorption from previous analysis. So when you inject from new sample, you bring that particular what we call contamination. So carryover problems you need to solve. So it will take some time as well. So you can also add one of the disadvantage, take some time to make sure that the syringe, okay, is available for the next injection, okay, or for the next extraction, okay. Alright, so low thermal stability, generally bleeding at high temperature, okay. The fiber is quite fragile, so if you use at high temperature, okay, for the extraction process or for the desorption process, it might damage the fiber, so it can cause the bleeding. It also have very low solvent stability. If you don't use the direct immersion, so you don't need to worry about it, okay. So the what we call the solvent can also damage the fiber, alright, and it's quite expensive. Normally 5 to 600, it can reach to 1,000 ringgit. In case of our recent case, so 3 fiber cost us around 6,000 ringgit, so it's very expensive, okay. So it's quite fragile, so you need to take care it carefully. That's why you need to require the expertise lah, okay. So you need to have very good experience, okay, to handle the SPME. So I think that's all. Okay, that's all the first part for the analysis of the what we call fire debris. Okay, the most important aspect that you are able to differentiate between the sample preparation methods, which is the best, so how it can suit your situation, how you can differentiate mechanism between the others, why this particular method has some advantage over the others, or how this method has disadvantages compared to the others. You need to understand why the step of the analysis as well. Begin by understand the problem, performing the literature search, selection of the method, performing the analysis, providing the data analysis, and then providing the discussion. Okay, then of course we continue with the sample preparation, okay, or the sample extraction. You need to understand why actually at the end we come to the SPME. Of course, this is the most established method available in the standard method. Okay, if you look at the journal or the published method nowadays, there are a lot more advanced method, okay, which is not yet been listed as the standard method. So I'm sorry about it. So see you again after a break, and then we will discuss on the part 2 in class. So I will give some sort of quiz in the e-learning, so you need to answer them before you can download the next chapter for the next class. Alright, thank you.